Alright, so I picked problem number 20 to do because it only has one dimension for net force. It's only going to have net force in the y direction. But even so, it's still a pretty tricky problem because it has two bars. None of your homework problems have two bars like that, so you won't necessarily need that technique, but it's still a good technique to um, to use for any of these problems. And so let me draw a picture real quick what it looks like. You can also look in your book. So it has two little cables, and bar, and then here it has two more cables sort of in a bit, and then a bar, and on this bar it has a little block. So I'm going to label these tensions. This will be tension 1 because that's what we're looking for. This will be tension 2. You might be thinking, shouldn't the tensions be the same? If this block was right in the middle, yes. But since it's more on this side, it's going to push harder on this side, so the tensions on this side should be greater. But we don't need to find those tensions specifically. We could later on, but we're just trying to find T1. So all four different tensions. There's the weight of this bar acting from the center of mass. The weight always acts from the center of mass of an object. And if it's a uniform object, the center of mass is halfway, it's right always in the middle. So this is a M1G. The weight here would be M2G, and the weight of the block, I'm just going to exaggerate the vector just so I have room to write it. It's not all cluttered. This is a M block G. We know that this distance is D from here to here, and this distance is D from here to here. So that makes things nicer, a little easier. We know the length of this bar, bottom bar, is called L2, and I think that's it. Let me just list the givens up here. M1 is 50 kilograms, M2 is 30 kilograms, M block is 20 kilograms. These are the givens. D is 0.5 meters. L2, length of bar 2, is 2 meters. And that's it for that. Alright, so because we have two bars, well, first off, earlier I stated that we need often two net force equations, one for the x direction, one for the y direction. But since these forces only act in the y direction, generally we would only need one net force equation for this. But, excuse me, we have two bars, and so we're going to need two y direction net force equations. So that's what makes this problem different than other problems you'll see, but still using the same technique. So I'm gonna say f net. Normally I would say like f net x equals 0, f net y equals 0, but here I'm gonna say f net y1. That's for bar 1 equals 0, and that equals the sum of the forces acting on bar 1. We'll call up positive, down negative, to the right positive, to the left negative, even though we don't need that for this problem. So up forces are T1 and T2. Those are pulling bar 1 up. So we'll say T1 plus T2. Down forces on bar 1. Well, we have T4 acting down, pulling down, T3 pulling down, and the weight of M1 pulling down. So that's going to be minus T3 minus T4 minus M1G. And we might as well take the opportunity now to plug in what we know. So this is T1 minus plus T2 minus T3 minus T4 minus M1 is 50 times 9.8. Alright, we'll just stop there, and then we'll do Fnet Y2 is 0. What are the forces acting on bar 2? Well, we have T3 and 4 pulling up, so that's positive, T3 plus T4. And we have two weights pulling down. We have M2G pulling down, so that's minus M2G. And we also have the weight of the block pulling down, minus MBG. Now you might ask, does it matter? Like, does it affect where the block is? Like, if the block's over here, would that be different than if it's over here or in the middle? For net forces, no. For torque, yes, because we have to pick a pivot for torque, and where this block is located will determine its distance from the pivot. But in terms of forces, all we're concerned is up, down, left, or right. So this is down, so we don't need to worry about whether it's down here, or down over here, or down in the middle. So there's that. Alright, and we know a lot of these values, so I'm going to do a couple things that you may or may not have thought of. See how there's a negative T3 minus T4 here, and a T3 plus T4? I can see that, this might be a good substitution to get, because I'm looking for T1, so somehow I got to get rid of T3 and T4. This might be a good way to do it. So just to keep these sort of same, these are both negative, I'm going to make these both negative just for the fun of it. So I'm going to subtract these over. This becomes negative T3 minus T4, and that's going to equal negative, so we know M2, that's 30 times 9.8 minus, we know MB is 20 times 9.8, and that's cool. So later on we're going to stick this up into here. But do we want to do that now? Yeah, let's do that now. So let's do that right now. We're going to take this and stick it into here. So let's rewrite this line right now. This is going to be 0. So this is right here. 0 equals T1 plus T2, and this is these two obviously equal this. So I'm just going to rewrite these. 30 times 9.8 minus 20 times 9.8, and then don't forget this one here, minus 50 times 9.8. I apologize for my groggy voice. If it's groggy, I'm doing this at 4:30 in the morning. What? And so let's solve for T1 plus T2. In other words, let's add all three of these over here. And while I'm doing it, I'm going to calculate these on my invisible calculator. So we get T1 plus T2 equals, and all of this happens to equal 980 newtons. That's pretty smooth. Alright, we'll use that later. Now let's do the torques on each of these. Normally we would only have one net torque equation regardless of how many, regardless of whether there was x direction forces and y direction forces like in this problem here. But here, since we have two bars, we're also going to have two net torque equations. So let's do that. The net torque on bar 1 will equal 0 because it's in equilibrium. And now we got to pick a pivot. So let's talk about pivot. Well, we want T1, so T1's got to be in there. So we really don't want to pick T1 as our pivot. We have other options. We could do a T3, we could do a M1G, we could do it T4, we could do it T2. My first instinct was actually either T2 or M1G, but then I realized, don't want, I got T1 and T2 in this equation, and so I probably don't want to get rid of T2 because I could use that as a system of equations. This is, I know both of these, M1 and G, that's just a number, so if I put it there, that would be getting rid of a constant that I know, which might not be useful. But I don't need T3 or T4, so if because I got rid of that using this net force equation. So I could pick either T3 or T4 to use as a pivot. I do know D, a distance D from T4, so that might make it easier to deal with in terms of a pivot than T3, because for torque we always pick a distance from a pivot point. So since they conveniently give us this distance, yeah, let's make T4 a pivot point. So that's the choice I made, is to make the pivots here and also here later on for the T-net2, torque net 2 pivot here. Yeah, so let's do it that way. Now again, don't be scared to pick a pivot point and realize later on it doesn't work, because just try a different one later on. No big deal. So with this in mind, then we got to think which direction clockwise or counterclockwise do these forces cause the bars to torque. So T2 going up that way is going to torque it clockwise, so I'm going to make clockwise positive and counterclockwise negative. And T2 is a distance D from the pivot if I make the pivot here. So this torque is going to be T2D. That was nice. And they're already perpendicular to each other, so I don't have to do like sine of any angles or anything, which is nice. Then we got M1G acting, and that's also clockwise. See if it's wrapping around that way, and it's also a distance D. No, it's a distance. Actually, if the length of this bottom bar is L2, and this is in the middle of this whole thing, then this is actually L2, half of L2. So we're going to do plus M1G L2 over 2. Do you see that? So this length of this bar is L2, and M1G is halfway in between that bar and here, so yeah. And T3 is also pulling down, which is going to make it go clockwise, so that's going to be T3. And T3 happens to be the whole bar length, bar 2 length away, so that's just L2. And then T1 is finally going to be the one that counteracts all three of these to make a counterclockwise torque. So we'll make that negative, and that's going to be T1. And that distance from the pivot is L2 plus D. This is also D here. Alright. And now we know a lot of these numbers, so let's just plug as much in as we know. So 0 equals, and D is 0.5, T2. I like to write numbers before the variables, so don't let that confuse you. I just put the D in front. Plus, we know M1 is 50. This is going to be longer than 15 minutes, I apologize, but I don't want to split this up. 9.8 is G, and L2 over 2, that's 2 over 2. Plus, and we know that L2 is 2, so this is 2T3. Minus, and this is going to be L2 plus D is 2.5, so this is minus 2.5 T1. Alright, so we're going to leave this alone for now, and we'll do torque net 2 equals 0. And we picked this as our pivot point. for the same reason as we picked this one. Although this one, now that I think about it, we know this is D also, so it probably wouldn't have been so bad to pick. Yeah, it would. We want to be consistent because we're gonna solve this TorqueNet2 for T3 and plug that up in here. So if we had a T4, we wouldn't have been able to do that, which you might not have realized at first, but at doing these, you would have like, oh, I need it. You always want to keep system of equations in mind when picking your pivot point, so that you can cancel things out more easily. So it's sort of an art form in a sense. You'll get the hang of it. I have faith in you. So anyway, if this is our pivot, then we have three forces causing torques. The mass of the block wants to pivot it clockwise. Mass of the bar 2, same. And tension 3 counteracts that and goes counterclockwise. So it's going to be M, B, G, D, because this block is a distance D from the pivot, plus M2G, L2 over 2, because the weight of the block acts at the center of mass, which is halfway down L2, minus T3 L2. And we know everything except T3, which is nice. So this becomes 0 equals 20 times 9.8 times 0.5 plus 2 is 30 times 9.8 times 2 over 2 minus T3 times 2. I didn't put that in front this time. Whoops. Anyway, you could do all this algebra, not a big deal. Solve for T3, you get T3, I hope this is still on the page, equals 196 newtons. That's pretty cool. By the way, we could now take this and stick it up here and find T4, and hopefully that would verify what I said earlier, that T4 should be a little bigger. I'm going to do that now, actually. Yeah, I got T4 equals 294, I think, so it is bigger. Yay! Anyway, so take this 196, plug it up into here, and we'd want to solve this for T1, basically, and use that in a system of equations with this. So I think I have room over here. I'm going to do that over here. So this equation becomes 0 equals 0.5 T2 plus, all this equals 490, plus 2 times 196 right here is 392, minus 2.5 T1, and so solve this for T1. Actually, we'll just call this 2.5 T1. So add the 2.5 T1 over, we get 2.5 T1 equals 0.5 T2 plus 882. Just add these two together. And then what I'm going to do is I'm going to solve this. So subtract T2 from both sides. So minus T2 cancels. Right? So I'm going to put that into here. 980 minus T1. Wait, what? No. Solve this for T2. Let's undo that. Whoa, too big. I'm going to pause this one a sec. Alright, subtract T1 from both sides. So we want to solve for T1, so it wouldn't be smart to get rid of it. So those cancel. So T2 equals 980 minus T1. We're going to stick that in here. So 2.5 T1 equals 0.5 times 980 minus T1 plus 882. Do some algebra, and you should get T1 equals 4 57.333 newtons. And that's the answer. Pretty cool, huh? Alright, so that's one down, two more to go.